coming again. So before I forget, so this is not going to end in a big theorem, because it's really a story that's going on, and it's largely work of Tim Large, at least the homotopy theoretic part. Tim Large is a graduate student of mine. You know, at Harvard, you know, when you're at the end of your PhD, there is sort of an exam where your thesis advisor has to explain that they understand their work to their colleagues. I always wondered what happens when the advisor fails the exam. Does the advisor lose the PhD?
Yes.
So luckily at MIT we do not have this, so I do not have to worry about.
Yeah, I have to tell you, I had this kind of problem when Zabrodsky was my student, was defending his PhD. I had this problem. I didn't forget almost last.
Okay, so we don't have this, so I don't have to worry about my PhD getting withdrawn. But that's not to say that I understand everything that I'm about to say. Okay, so let me first say where this comes from. Okay, what is the concrete? It's always nice to have a concrete problem that we're trying to solve, right? So I will look at non-compact symplectic manifolds. But I will look at, general theory of non-compact symplectic manifolds is not very nice, but so I will look at what are called Liouville symplectic manifolds. So this means that they come with a vector field which rescales the symplectic form. So in particular, the cohomology class of the symplectic form is 0 here, and so it's this and so what do we want? What do I want? So so I want the flow. This should exist for all times. And I want the flow to sort of flow outwards outside a compact subset. So this means that you have a function which is proper, let's say bounded below, let's say this, proper, and such that outside a compact subset it's kind of flow outward. So what happens is that there's some topology here, and then there's the region at infinity, and the region at infinity is just sort of an exponentially increasing infinite cone. Okay?
So you say there exists F?
Yeah, there exists F, yes. Yeah, there just exists F. Whereas, well, it doesn't really matter, because everything I write down will eventually be actually just invariants of the symplectic structure. Okay. So the examples. Okay, so if I have a cotangent bundle of a closed manifold, and this is the fiber-wise expanding vector field, and everything is good. So another example would be, any smooth complex affine variety with a suitable, say standard.
If it's a projective mode, then affine variety.
Sorry, it's complex. It's an affine variety. It shouldn't have, because the symplectic form needs to be exact.
Yeah,
so I cannot have
it. Like homogeneous case.
Yes.
If I can. If M it's a projective map to and define
A
variety.
compact
No,
doesn't.
because the symplectic form has to be exact. So if you blow up a point, it is no longer, okay? In part because, you know, a lot of things in symplectic geometry depend on the homology class of the symplectic form. So if you assume that is 0, then you kind of, things become scale invariant, and the theory becomes a little bit easier, okay? So the, well, not the main invariant. One is a symplectic invariant, is what's called symplectic homology. Okay. So I will not describe how to define it because it takes too much time, but I introduced Hamiltonian Floer homology, so I can say that this is the direct limit of Hamiltonian Floer homology. Over a sequence, well, over simply increasing Hamiltonians, unbounded. So, Hamiltonian. And I'm not going to say exactly what the classes of Hamiltonians or how you form the direct limit. But let me explain to you a couple of examples. Okay. So, so this somehow has to do with Hamiltonian dynamics, and sort of not surprisingly maybe on a cotangent bundle. It has to do with the cohomology of the free loop space. Okay? Because the Hamiltonian dynamics on T star n is the geodesic flow on n. So more precisely, this is a manifold of dimension n. And just so that I don't mess up things, I'm assuming that n is orientable. Okay, and okay, so it's essentially the homology with some shift. It's actually the, the homology maybe of some Thom space over the loop space, and then comes a small but extremely important addition to this. So what is this? Okay, so you have the second Stiefel-Whitney class of n. Okay. So then you transgress it so you pull back by evaluation and so on. That gives you a class here, and -1 W1 bar is the associated local system. Okay. So by the way, yeah. Okay. So at the moment, so as usual, symplectic homology can be taken with any coefficients, but at the moment, let me just use integer coefficients, so I can put any coefficient system and carry it through, and here there should be a 2 instead of a 1. Okay? So associated to this class here is a local system which, flips the holonomy to ±1, and this is the homology twisted by this local system. Okay? So this, I think the first person to recognize this fact here was Thomas Krag, and this is kind of important. So for instance, okay, so the symplectic homology of T star CP2, which should be the free loop space of CP2, but CP2 is not spin; it has non-zero second Stiefel-Whitney class, so is a 2 torsion. Okay, so having this twist here changes the group considerably. Some other examples, which is slightly less exciting maybe. the symplectic homology of R2n is 0. And in fact, symplectic homology satisfies a Cohen formula. And from that, you can see that, in fact, the symplectic homology of anything cross R2 is, of course, 0. Okay? This we're okay with because the symplectic topology of these things is actually not particularly interesting. Okay. All right. So this is not the only invariant for these. These open symplectic manifolds have a lot of, non-compact symplectic manifolds have a lot of structure. But this one happens to be one, this invariant, that we kind of got used to. It's got, you know, in some sense intuitive, it has interpretations and mirror symmetry and other things. And so, you know, it's kind of a yardstick to how we got to do this. So, okay, so it's easy. Okay. So okay, right. Let me. Okay. So what is the situation here for these invariants, right? So. So the first thing that happened sort of was that people understood that, you know, the topology of M is relatively irrelevant. So it's easy to find examples which are diffeomorphic to R2n. They have no topology, at least in high dimensions, and the symplectic homology is non-zero. So in particular, they're distinguished from R2n, and they're distinguished from each other, and so on and so on. They're not maybe the most natural examples, but they definitely exist. Okay? And then what happens is that, you know, we started getting better constructing these manifolds, and I'll explain in a second how we construct them. And then as we went through these constructions, right, it seems like the opposite happens from what we thought it would, which is that sort of generically it seemed that this invariant would be 0. Okay, so lots of cases we construct something, then you compute it, and then it turns out to be 0 unless you arrange for special things to happen. At first this was not very well understood. So here, now we understand that it's in part because you know, if you do something, so there's something called flexible one-state manifolds. And this is a very, in principle, if you construct it, you could get something flexible, and so they are completely classified by homotopy theoretic data. Let's say if you know the symplectic the underlying manifold as a differentiable manifold, and you know the class of the tangent bundle, the abstract symplectic vector bundle, then that determines everything if it's flexible. And so, but there's a middle region here where the symplectic homology and other invariants tend to be 0, but we don't quite know what is happening. Okay. And so the question is, you know, how thick is the line between those two, and what is actually sitting in the middle between that line? So I want to give you a concrete example here of how we construct these things, even though maybe I will regret that I did it, but okay. So
the fact they completely classify the homotopy is a kind of the Gromov's principle applicable.
It's right. It's a very, very complicated application of Gromov style H principle argument. Okay, and you know, this is due to, so, okay, so this, well, I will not give you the history. Okay, so, so one reason why it's, so we can construct these things by gradual handle attachment, okay? And as a special case, of this, it's what I call a construction by Lefschetz thimbles, which is inspired by sort of Picard-Lefschetz theory that analyzes the topology of complex algebraic varieties. Okay? And so you start with a manifold of dimension 2 lower. Okay? And so this is sort of, okay, and plus Lagrangian spheres. Okay. So
They don't intersect?
they can intersect. They can completely intersect because the way that you do the, you know, you go up by 2 dimensions. So you start with, say, F cross a 2-dimensional disk. And then here you put your Lagrangian submanifolds on the boundary of the disk. Okay, and so on. And then, well, topologically speaking, these are n-1 spheres, right? So you attach an n-dimensional disk, and then you kind of, well, that's not a manifold, but you attach actually a piece of a vector bundle over a 1-dimensional disk. Okay? And so you can take any spheres that you want, any finite number. You can take the same sphere several times, and you can get a manifold. And we know pretty well how to compute the invariants once things are constructed in this way. Okay, so
these arms are what called Lefschetz thimbles?
well, these things, the ends are well.
In the picture, what is a thimble?
Okay. The thimble would be the fiber of the vector bundle.
Ah, okay.
So that going in the other direction, going out to infinity. Okay. So the symplectic homology of M depends on. So what I used yesterday is I used a Lagrangian Floer homology of with itself, but there's also Lagrangian intersection Floer homology. So we take 2 Lagrangians and you study how they intersect. This gives you these groups here that carry some additional multiplicative structures and so on. And these groups with this structure determine the symplectic homology of M. Okay. So this takes place inside F. So you go from 2n-2 dimensional data to 2n dimensional data. Okay, so now. Okay, so all right. So I want to start with Sn-1, and so here I want to choose some open domain with smooth boundary. Okay, and then inside du, so this is a hypersurface, right? I want to choose some v here open, and again dv smooth. So you have the u, and then here you have some kind of v. Okay? And so here is a picture of F. Okay? So I will start with the cotangent of Sn-1, and then I will put in another this is graph, sorry, df, f is some function of u. So the graph here is another Lagrangian submanifold. So this one here, so here you have an S minus 1, which is the 0 section. And this function here is essentially designed so that it goes to infinity at the boundary. So the gradient goes to infinity at the boundary of u, except at v, where it sort of goes to minus infinity. So it sort of goes to infinity here, except when you approach v, it sort of goes the opposite direction. Let's see. Sorry, and then complete. Another Lagrangian sphere. So I'm going to add a piece to the outside of my manifold. I'm sorry if this is not. So it's T star Sm together with this piece here. And it contains these two Lagrangian spheres. Okay, let's call them L1 is the 0 section, and L2. And what you need to know here is that I can arrange, the only thing, I did not explain this construction very well, but what you need to know is that you could get the Floer cohomology of these, because it's given as a graph, is just the cohomology of u rel v. And if you think about it, I just gave you a sphere. If I gave you a sphere of very high dimension, you can put an open thing having the topology of any complex, and a v to have the topology of any subcomplex. So this can be, if you allow n large, this can be pretty much any finite CW pair, whatever you want to call it. Okay, so this can be pretty much anything. And then so this is f. So use f, and so one of these. So I'm going to use two things here. I'm going to use the 0. So here I said I need to use spheres, and here it makes it look like as if I used L1 and L2, which I do not want to do. So in fact, I want to use these things here. So this one here, I didn't introduce this notation, this tau here. So one reason why this construction is very nice is because every Lagrangian sphere comes with this automorphism of f, which is the Picard-Lefschetz transformation. So here's the Picard-Lefschetz. So once you have a sphere, you can make more. You can say spheres. You can make more spheres by just applying these transformations. So I use these two here to make Lefschetz symbols, and we construct here. This gives you m. And so what happens here is that the symplectic cohomology of m is either, so if h star uv is non-zero, it's 0. Okay? And if h star uv is 0, then it's the symplectic cohomology of T star Sn, which is the homology of the free loop space of Sn. So in this case, it's not twisted because the sphere is spin.
How is V related to the critical set of F? Is it like?
No, well, you think about, it's like the Morse theory of F, but F is unbounded, goes to minus infinity.
But
So-
is V related to F in some way, or is V?
Excuse me?
Is
V is the
related to
set where F goes to minus
okay,
infinity.
yeah,
Okay? So
Exactly.
the cohomology of U rel V is the cohomology that you get from the Morse theory of the function F. Okay? So this explains what I said at the beginning, which is that somehow when you do these constructions generically, right, which is the non-zero case, the symplectic cohomology becomes 0. Right? And then there are so it's not, if you want it to be non-zero, you have to arrange things to be special. In this case here, you have to arrange this to be exactly 0. Okay? And so this is always the same, and it's gigantic. Okay, so this is my example. All right, now, okay. So my problem is, you have all these cases here where the symplectic cohomology is 0, and a priori they all look different. Okay, but so the question is, are they here or are they here? Okay, if they're here, the symplectic cohomology is 0 because it's actually not interesting. what I've constructed. If they're here, then God knows, because we have no idea how big this intermediate territory is. Okay, very good. So,
so again, so you construct examples of manifolds, vector manifolds, or the real manifolds.
the symplectic homology is 0. So mostly this is like one case, right? You can choose essentially the input of this. I mean, I did some kind of stuff. I did some kind of stuff, but the input was a sort of a topological pair, like a CW pair. But whenever the homology is non-zero, the symplectic homology is 0. Okay, so it's sort of if you build a random CW pair, you expect the homology to be non-zero, right? For whichever sense of random. But here it's sort of the opposite. Whenever the homology is non-zero for the sort of generic choice, the invariant sort of does nothing. All right, so let me be a little bit of a homotopy theorist. Okay, so all right. So my colleagues in homotopy theory at MIT reliably assure me that I am not a homotopy theorist. So remember now I'll be a homotopy theorist. So I will work mostly with pointed spaces. Or if you don't have so if you have a point space that's not pointed, then I will add artificially a base point, and I will work with with the wedge product of pointed spaces, which corresponds to the ordinary product of unpointed spaces, and in particular with suspensions. And with in the sort of stable homotopy category. So even if I had ordinary pointed spaces, I would want to suspend them when I form the maps. And in fact, in the stable homotopy category, there are category of spectra, this map sigma becomes invertible, so you add formal kind of desuspensions of objects. Okay, so given. So now this stable homotopy category is a kind of algebra, right? So for instance, you can sort of reduction mod P. Okay, which is so it's the it's a sort of mapping cone of the map P from X to X. Or if you're not a homotopy theorist, you might want to say like this. Okay. So you take the degree P map from S1 to S1. And you form its mapping cone, which means that you attach a two-dimensional cell, okay, along this thing here. This is called the Moore space. Then you wedge it with that, and then I will desuspend it again. Okay, because you have to do it this way. There's no honest map that's P from S0 to S0 because S0 is essentially a point. Okay, so and so this one here, this has for instance, the homology of X mod P. With integer coefficients is the homology of X with coefficients in C mod P. Actually, it doesn't matter if P is a prime, okay? Or so this is reduction mod P. It doesn't quite work the way you expect it in algebra. There's some tricky things. The things that also works, or you can invert P. Which is some sort of direct limit of slightly more complicated, but the homology of X, the inverse with coefficients in Z, would be the homology of x coefficients in Z1 over P. Okay? If you're a homotopy theorist and it's completely wrong what I'm saying, speak up. All right. So this is an example of localization, and this here is inverting some P. Okay. And so I want to look at something particular, which is the Adams V1 maps. This is interesting. Okay. So the Adams V1 maps. So they are. So you take this the sphere. Okay. 2p. 2p minus 2. Again, this is stable homotopy theory, so you might have to suspend it. And you reduce it mod p, so it's really this kind of Moore space there, and S0 mod p. So this is this map V1. Okay. So for instance, the homology of this one here is just Z mod p. The homology of this one here is also Z mod p, but in different degrees. So this map clearly acts trivially on homology. Okay? But it's actually a non-trivial map. In fact, what happens is that, so this is odd p. Okay? So what happens is that it's actually not even nilpotent. So if you take topological K-theory and you apply it to this, this is actually an isomorphism. Okay? So for p equals 2, so this is I don't know what is the prehistory of chromatic homotopy theory or something. So this is it proves the superiority of K-theory over this one here, so okay. So there are these maps here that so in particular it means that having an isomorphism on K-theory, it's an interesting notion. So there are spaces which are definitely not not the same, but have an isomorphism on K-theory. In particular, okay. By taking Cohen V1 or V1 to the 4 for p equals to 2.
I don't understand what raising the power. It's not map from space to itself, so I don't know what does it mean.
It's a map from a space to sorry, say again?
It's not a map.
Oh, I'm sorry, but you can iterate it, right? Because this is a stable map.
Okay.
So
Okay.
it's a
All right.
if it existed, it would be a map from S2 to S0. Its fourth power, it exists as a map from S8 to S0, which behaves like the fourth powers of the other maps. So V1 itself doesn't exist for the prime 2. In particular, by taking the kern of V1, we get a space. So, well, a space, really a spectrum, but let's say which can be realized as a finite CW pair XY. Okay. So such that, or maybe I could collapse Y. Okay. So let's get a space. Okay. Space X, pointed space. Pointed space. Such that, so if I take the cone here, okay, such that the K-theory, well, it's a pointed space, so the reduced K-theory of X is actually 0, but the cohomology of X is no. Cohomology is, so reduced cohomology is okay. So of course, the cohomology and topological K-theory are isomorphic rationally, okay? But then it is possible for a space to have a non-trivial cohomology, but a trivial K-theory. Okay? right. Are we good? This is as much homotopy theory. So now I need to tell you, to talk a little bit about generalized cohomology theories and their role here. Okay? So. So suppose I have a space that's made up in the simplest possible ways, okay? From two cells, okay? Alpha is, oops, plus 1. Alpha is Sn plus n. And is the attaching one. So, and I want to compute, let's say, the homology of X. So, okay, so this is, there's the usual short exact sequence, and this one here is H star minus, well, and this one here will be, sorry, there's some, I put in a shift by 1 here. Which you'll excuse me for. So this goes to this degree goes down to 1. This. And so you need to know the degree of alpha in order to compute the homology. Okay? I hope this is not a mystery. Okay, good. So what if I wanted to compute, say, the stable homotopy theory? So then, okay, E n plus n plus 1, n. Okay, sorry. Okay, star minus n plus n. Okay, so okay, so now I need the attaching class of the attaching map of a in terms of stable as a stable homotopy theory class. So let me say it like this. Let's suppose that this is a differentiable map, and I say that A is alpha inverse of a point, which is a submanifold, okay, of dimension n. Then this degree here is just the number of points in A. Of course, if A has dimension greater than 0, then this is nothing. Okay. Now this one here is A as a framed Bordism class. Okay. So which means A is not just a manifold, but because it's the preimage of a point, its normal bundle comes with a canonical trivialization. And so you need this here, the class of this here in framed Bordism in order to reconstruct the stable homotopy of X. Okay? And for instance, for K-theory, or complex Bordism, if we wanted to instead use, say, K-theory or complex Bordism, so we need a, well, let's say for K-theory, K of X, need A up to some sort of Bordism, which corresponds to K-theory, let's say spin C Bordism, or Bordism as an almost complex manifold, that would be enough. Instead of frame, so the normal bundle doesn't have to be trivialized, you just have to have a reduction. Okay? So depending what you want to compute, you need different amounts of information. And the reason why I'm explaining to you this simple fact is so remember, this flow cohomology is a kind of Morse theory. So it is a little bit like building things out of cells. So we have this one here. Okay, so this is symplectic cohomology. And you could ask, for instance, do you have a stable co-homotopy, in fact? Or do you have an underlying spectrum? Well, it's a direct limit, so it will probably be like a pro-spectrum, or is there, symplectic K-theory? So when you look at this, you're trying to reproduce these computations in terms of framed Bordism classes, and it turns out that the spaces that you need actually do not satisfy the same conditions as in ordinary topology. So this one here, generally speaking, does not exist. Okay. So only if the tangent bundle of M can be written as has a Lagrangian distribution. Which means tangent subspaces, which are Lagrangian at each fiber, which form a subbundle. Okay? And even then, there could be many different homotopy classes of Lagrangian distributions, and each of them gives rise to a different homotopy type. Okay? But this one here actually always exists. Okay? Because the spaces that you're dealing with, which are as usual some sort of version of holomorphic maps, they are always stably almost complex. So we have cohomology, we have K-theory, we sometimes and very non-uniquely have a Floer homotopy. And this is where the things become interesting. Okay? Right. Now, all right. Now I'm getting back to this one here. Okay, and I'm going to use the prime 2 for reasons that you are going to see in just a second. Okay? So I will construct as follows. Okay, so using so it's like this, H star UV, which has only 2 torsion, which is 2 torsion. Okay? So this means 2 torsion here. Okay, so I'm going to choose my pair U and V, which I can whatever, so that the relative cohomology is vanishes at other primes. It's and so then if you look at this one here with coefficients Q, of course it's 0, or okay, hold on, I'm slightly confused. Okay, good. So it vanishes at all primes, so that means that the symplectic cohomology of M, right? This is so it's the opposite. It vanishes. One vanishes when the other doesn't. symplectic homology of M with Z2 coefficients is actually 0. Okay? Maybe I should just use C1Q. Okay. So in other words, if you do ordinary symplectic homology, which is symplectic homology with MZ, okay? So you do this with integer coefficients, is 2 divisible. Okay? So every element has a unique, you can divide it by 2, which is a very strange thing if you think geometrically, because generators of symplectic homology have some kind of dynamical interpretation, and so it is 2 divisible. Okay? So this is, I have done something which is non-zero at all other primes. So now this one here, which I put up here, this is 2 torsion. And this one here is 2 divisible. This one prime. So then if you take that tensor product and by the Kuhn formula, this one here is 0. Okay? Completely, no matter which coefficients. Because this one is 2 torsion and then there's 2 divisible. So okay, this is maybe completely unfair, okay? Because you have the feeling, okay, I did some algebraic trick, right? So this one here certainly has a lot of non-trivial symplectic topology. This has a lot of non-trivial symplectic topology. It just happens to be concentrated at different primes. And so when I try to combine them, boom, and everything goes to 0. So this is the example the kinds of examples that I want to look at. So far I haven't specialized too much what I want to do. But I actually here, I want to use something specific. Use UV so that so U divided by V is isomorphic to the mapping curve of the atoms. S8.2, D1.4, S8.2. Okay. So this is 2. This certainly satisfies the fact that this is, this only is 2 torsion, so I use this particular space. Okay. So then what happens here? Okay. So note that. So this one here, so the Floer homology that enters here is the homology of U rel V is non-zero, but the corresponding K-theory calculation is 0, right? So that was the whole point of this space, that the K-theory is 0. So if I did this in terms of K-theory here, right, then it cannot, it's actually, I'm in this case here in terms of K-theory, and so we know in this case here, okay, so we know that the symplectic homology of M prime is actually 0. And if you've been following this, you'll see that there's a certain logic to these things. Okay, so if I did it in symplectic K-theory, that the symplectic K-theory here should be non-zero. Okay, it's probably 2 torsion. Okay, so this is distinguished. This is because if you did the K-theoretic computation in K-theory, or in this case here, the homology is 0. So the symplectic K-theory of this one here should be non-zero, and to the extent, so I use this cross CP2, so I have to also show that the symplectic K-theory of CP2, so it needs needs. Okay, so that the K-theory of UV is 0 implies the symplectic K-theory of M is non-zero, so this would be the analog of that one here, and it needs symplectic K-theory of M1 cross M2, the Künith formula. Well, K-theory is, in the same sense as the ordinary Künith formula holds. K-theory is relatively nice with respect to Künith formula, and then it also needs that the symplectic K-theory of T star CP2 is non-zero. Okay, so these are the three ingredients. I think they're all sort of reasonable. As you can expect, our computational methods for symplectic K-theory, it being a complicated thing to construct in the first place, are not particularly great. So at the moment, these are all conjectural, but so they all require some kind of different generalizations of things that we know to do in ordinary cohomology. Okay, so I should say a couple of things to end. So the first thing is, why is it this obviously, in ordinary cohomology, this is impossible. If the ordinary cohomology is 0, the K-theory has to be 0. Because there's an Atiyah-Hirzebruch spectral sequence. Okay? So if ordinary cohomology governs, in the end, the size of everything from above. But the symplectic cohomology is a direct limit. So it's sort of like a pro-spectrum. So you run into convergence trouble with the Atiyah-Hirzebruch spectral sequence. And it is absolutely not the case that it would follow that this thing here is a priori completely possible. Secondly, suppose that this very contrived maybe example works out. Well, what would we do next? Well, so the whole start of all this was this Adams map V1, which is trivial in cohomology but induces an isomorphism on K-theory. Okay, so. And it gives rise to this Adams space X. So at least in P local homotopy theory, after you do this, there's another self-map of this Adams space, which is trivial in K-theory, but is detected by on chromatic homotopy level 2, so by things like Morava K-theories. So the next stage would then be that there would be spaces which have trivial symplectic cohomology and trivial symplectic K-theory, but possibly would be detected by non-trivial symplectic, other generalized symplectic cohomology theories. I cannot really pronounce on that, but so, remember I drew this diagram with this dividing line, and it's possible that this unknown region is divided into thin slices by sort of a homotopy theoretic classification of exactly how deep you need to go homotopy theoretically to get something to be non-zero. And I will stop here.